for this. Okay. Let f be the continuous function defined on negative 4, 3, whose graph consisting of 3 line segments and a semicircle centered at the origin is given above. So that is f. Let g be the function g of x is equal to the integral from 1 to x of f of t dt. Find the values of g of 2 and g of negative 2. So if you wanted to find g of 2, all you're doing is you're plugging in 2 into the function. So it's the integral from 1 to 2 of f of t dt. So it's the area under the curve from 1 to.
But I didn't understand.
This is the area under the curve from 1 to 2. That's what it means. So you're going from 1 all the way to 2. So you're just finding that area right there. There it is. The area under. So what is that area? It's negative a half. Yes. So what about g of negative 2? What about g of negative 2? You're going from 1 to negative 2 of f of t dt, right? So which way are you going? You're going left from 1 to negative 2. So you're doing from 1, you're going backwards. We're at negative 1 now, but then we are also this, right? Is that wrong? 1/4? Why? Oh, is it 1/4? Did you do your math wrong, Keaton? Base times height. It goes over 2, and it goes over 1, and then how high does it go? 1/2. It's 1/2 high. Look at the scales. Look, this right here is y equals negative 1/2 right there. So it's 1/2 times 1/2. No, it's a line. They tell you it's a segment. It goes over 2 and down 1, so it's a slope of negative a half. So it's negative 1/4. Okay, hold on. Let's keep going here. So we're going from 1 to negative 2. We're going backwards. Kids, don't care about the or right now. Just want to do this. Yeah, go ahead.
It was easier to just flip the sign to be negative from 2 to negative 2.
Yeah, you could. Yes, if you want to do it that way, that's fine too. Yes, this is equal to, if you want to do this, negative 2 to 1, but you have to put the negative on the outside. That's absolutely true. I'm sorry, I thought you were referring to the prior question. You don't have to, but it's just easier. Some people like reading the integrals from left to right. We switched the limits of integration. If you flip them, sorry, it just went away. Yes, if you flip them, you make it negative. Yeah, that just makes it so you can read it from left to right, which is totally fine. So what's the area right there? This is just a base of 1 and a height of 3. So it's going to be 3 over 2. 3 over 2, right? And then you have to subtract this. What's that going to be? Pi r squared all over 2. So what's this one going to be? Oh, I hate it when it blinks like that. Oh, man, it's the layers. I'm sorry. For some reason, this has this funky layer issue sometimes. It's going to be what? 3 over 2. It's going to be negative 3 over 2 minus pi over 2. So what's that going to be? You just say it's going to be pi over 2 minus. Yeah, that's really annoying, I know. Pi over 2 minus what? 3 over 2. Yes. Does that make sense, everybody? Does that make sense? Yeah, hold on a second. Okay, does that make sense on that first one? That would be 2 points. Yes, because it's below. You're going from left to right, and it's going below. Yes. So let's find them. Yeah, you overthought it a lot. Okay, probably, because it's not that bad. G of x is equal to the integral from 1 to x of what? F of t dt, right? So what is g prime of x? F of x. What is g prime? No, it's not capital F of x. It's f of x. What happens when you take the derivative of an integral? What happens to the integral? Goes away, becomes f of x, right? Becomes f of x. Now, there's actually an invisible thing right there. What's invisible that's right there? A 1. dx over dx, a 1, because you're doing the chain rule, but you're doing the chain rule on x, so it's kicking out a 1. It's important to know that, because if this was x squared, what would you have to kick out to the outside? A 2x. But that isn't squared, so you don't put a 2x out there. So if g prime is f of x, what's g double prime of x? F prime of x, right? So it's asking you for g prime of negative 3. So that's going to be f of negative 3, right? So you just go up here. What is f of negative 3? What's f of negative 3? Sorry, f of negative 3. Whatever that point is right there, right? What is it? 2. It's 2. And then what's g double prime of negative 3? Is f prime of negative 3. What is the slope right there? Yeah, that slope right there is negative 2, 2. And that slope right there is 1. Done. There's your 2 more points. Sorry. This right here must be a constant for the fundamental theorem of calculus to apply. Does that make sense? Okay. Side note, this is not part of it, but let's say you asked this, right? Let's say I said, and this is a side note, so I'll try to break this up a little bit. Let's say I said j of x was equal to the integral of x squared to x cubed, I don't know, of f of t dt, what do you have to do? You have to break it up. And what constant can you choose? What can you choose? Anything you want. Now, theoretically, do you have to pick something between x squared and x cubed? No, it doesn't matter which one you pick. It does not matter. It does not matter at all. What you're essentially doing is this. Look, if you have a function and you have, here's your function right here, and you're integrating from there to there, right? So let's get going from a to b. You could break it up and put a c there. This plus this obviously equals the integral from a to b. Do you agree with that? But let's say I picked a c value that was outside there. So let's say instead of the c value there, let's say the c value was over here, and you went from a to c to b. Look what happens. First, what would you do? You would go backwards, and that would be what? Negative. And then you would go forwards from there all the way to b. What cancels? C to a cancels, leaving you with just what? A to b. So that's why it doesn't matter what you choose. So it doesn't really matter what you choose on a lot of levels because you never really evaluate. Well, sometimes you are. So what's a good value to choose? Or 1, yeah. 0 is great. So sometimes 0 poses a problem, but in this case, you know that this is equal to x squared to 0 of f of t dt plus, we're not done yet, x cubed of f of t dt. And we can't quite use the fundamental theorem of calculus yet because we need the constant on the bottom, the variable on the top. So this would equal integral from 0 to x cubed of f of t dt minus the integral from 0 to x squared of f of t dt. Now you could apply the fundamental theorem of calculus. Like if you wanted to do the derivative of this, what would j prime of x be? F of x cubed times what? 3x squared minus f of x squared times 2x. There it is. Does that make sense? So that's your side notes. Let's go back to the question. Find the x-coordinate of each point at which the graph of g has a horizontal tangent. So let's just stop there. Let's do that first. Find the x-coordinate of each point at which the graph of g has a horizontal tangent. So you have g of x. When does g of x have a horizontal tangent?
When the derivative equals 0.
Has horizontal tan when what?
The derivative equals 0.
When g prime of x is equal to 0. So we know that g of x is equal to the integral from 1 to x of f of t dt, right? So what is g prime of x equal to? F of x. F of x. It's important that it's x. F of x, right? So if we want to solve this, we're looking at it when f of when f of x equals 0. So we want to examine f of x equals 0. So what are those true? Look, tells you right here. Where is it? -1 and 1. So x is equal to -1 and 1. So we just answered the first part of that. Now go on. What?
That is like a perfectly straight line. Just take a screenshot or something.
Not bad. Thank you. Okay. For each of these points, determine whether g has a relative minimum, relative maximum, or neither relative minimum, maximum at that point. So how do you find out if it has a relative minimum or maximum? There are two different tests we could do. You could do the or the. Which one do you want to do? Yeah. Why wouldn't you do the second derivative? What's the primary reason you don't do the second? You can do the second derivative test if the second derivative is easy to find, right? So but hold on. What is, listen, kids, we know what g prime is, right? What's g double prime? G double prime is just f double prime of x, right? So f prime, thank you. Just f prime of x. So these are the values we think there's a relative min, max, or neither, right? So what do we need to check? Just g double prime of 1, which is f prime of 1. What is f prime of 1? Look at your graph. What's f prime of 1? It does look like it's a corner. So we'll come back to that in a second. And what about g double prime at -1? That's f prime at -1. What is that? F prime at -1. What is it? It's a corner. Look, what is the derivative right there?
Oh, that's where we're looking?
Yes, that is f. Well, what's the derivative there is what I'm saying. What's the derivative there? It doesn't exist because the left-hand derivative is different than the right-hand derivative. And what's the derivative right there? It doesn't exist. Does it exist? No, because look, the left hand, it's going to be, this looks like if you're coming on that graph, on that curve, what does it look like the tangent line is going to be? Vertical, right? But if you come at it from the right, it looks like it has a slope of -1/2. Does undefined equal -1/2? No. So if we looked at this in the second derivative test, it looks like it's a, are they, what do you think the answer is to this? Okay, the question is asking for each of these points to determine whether G has a relative minimum, maximum, or neither at each point. So what do we think? Neither at both. How confident? Analysis is not incorrect here. Kids, Frank, hi. Our analysis is incorrect. If you try to find the derivative at -1 and at 1, what happens? Bad things. Okay, so that was the first derivative. That was the second derivative test. What's the first derivative test? See if f prime. See if the derivative changes sign, right? Thank you. You're absolutely right. I'm so sorry. No, you're right, but it's still a corner though, because look, it's a semicircle below and it's a line above that, right? It's going to come to a point. So let's just look at it from the first derivative test. So I'm going to have to reconcile this in a second, okay? I have to come up with some sort of caveat to that second derivative test, which I don't remember at the moment. Let's go back to the first derivative test. The first derivative test, you need to test either side, right? Does the first derivative change sign? That's what we want to know. So look. But let's look. So if we do the first derivative test, values, x equals 1 and x equals -1. So what we're looking at is, at x equals 1, we're looking at we need to look at g prime of x, right? But what is g prime of x? That is f of x, right? So we need the sign of f of x. So the function at 1, the function is negative to the left of 1, and immediately on the other side, what is it? Negative. So at 1, it's negative here, and it's negative there, right?
On the opposite side of 1, isn't it positive to the left?
No. This is f, correct?
Yeah.
Look at the value 1. You see 1 right there?
Yeah.
The function to the left is negative there and negative there. It is below the x-axis. We're looking at the function itself.
Okay, I know we're talking slow.
So this is the first derivative test. So what can we say? It has neither, because it goes from negative to negative. It needs to change, right? If it goes from positive to negative, it's a maximum. If it goes from negative to positive, it's a minimum. So let's look at -1, though. What happens at -1? At -1, so at, I got to change color here, x equals -1. This is, again, f of x, because g prime of x is equal to that. To the left of -1, it is positive, and to the right, it's negative. So this means neither, because it doesn't change sign. And what about this one?
Minimum or
Maximum.
It goes from positive to negative. So it's a maximum. That's interesting. The thing I have to reconcile here is the following. Our first attempt here, what was our first attempt? Our first attempt was to use the second derivative test, which we think of as, if the second derivative is negative, it's a frowny face, so it's a maximum, concave down, so it's a maximum. If the second derivative is positive, it's a happy face, so it's a minimum, right? The problem here is that the second derivative, what happens at, it doesn't exist at those points. It doesn't exist at those points. So I need to go check the second derivative test to find that there's one caveat to it. I'd imagine you can only use the second derivative test conclusively when it exists at the point. Conclusively. So I think just because the second derivative isn't defined doesn't necessarily mean that it's neither. I'll have to check it. For -1 to 3, find all values of x for which g has a point of inflection. For which g has a point of inflection. So what is a point of inflection?
it's when it changes.
Second derivative changes sign.
Inflection point. You both said the great things. It's when it change of concavity, and that's when the second derivative changes sign.
Yeah.
Just because it's 0 doesn't mean it's going to change sign.
But isn't
No.
wait,
Just because the second derivative is 0 doesn't mean it's going to change sign at the derivative.
no, but don't you like,
You'd use that as a first step. It is necessary, but it is not sufficient.
but
It is necessary, but it is not sufficient. If you say the point of inflection, is where a graph has a second derivative equaling 0, you are wrong, because that is not always true.
no, I meant
Look at this and say to ourselves, let's just get another picture of this graph. Let's do that. Hold on. So this right here is f, right? This is f, and we know that g of x is equal to the integral from what? 1 to x of f of t dt. So g prime of x is equal to f of x, g double prime. It's important because you will get it wrong on the AP exam if you say f of t. G double prime of x is going to be f prime of x. F prime of x. So let's look at this in these regions here. From here to there, and I'll try to make better lines here, seems where the slopes change. So on this first region right here, and let's say, oh, it changes right there as well. From here and here, on the green regions, what can you say about f prime? F prime of x looks like it's going to be positive there and positive there. What about from here and there? What about those two segments there? It looks like it's going to be negative and negative. And then also from here to here, what is it going to be? Negative. And we know that this right here, f prime of x, is g double prime of x. So at what points, at what values does it look like the second derivative changes sign?
X equals -2 and x equals 0.
0 and x equals 1. Let me check one thing. It says the temperature at 20 is 71, right? So if you have 71, so you know that at time equals 20, the temperature is 71. You want to figure out what the temperature is at 25. So you need to find the net change from 20 to 25. Overall, if it's gone up 5, the temperature is now 76. Overall, if it's gone down 5, the temperature would be 66, right? So how do you find the net change from 20 to 25? You do the integral of what? Of the rate of change. And the rate of change is w prime of t dt, right? So what are you doing? The temperature at 25 is going to be 71 plus the integral from 20 to 25 of 0.4 square root of t cosine 0.06 t dt. Because what does this represent right here? That's the net change in temp from what to what? From what to what? From time equals 20 to time equals 25. That just tells you the net change. Does that tell you what the actual temperature is? No, it just tells you how much the temperature has changed. For example, if you had the velocity function of a car from time equals a to time equals b, how do you figure out how do you figure out the net change in position? You integrate velocity. If you integrate velocity, you get the net change in position. For example, if the velocity function is symmetric and positive one way, negative the other, when you integrate it, you'll be in the same place if it's perfectly symmetric. But the idea is if you integrate the rate of change, you get net change. Does that make sense?
Actually, graphically, it made sense to me in my head.
Cool? Good. Okay. What can you actually figure out? You can find the rate of change at each of those values. So you can find dB dt at time equals, at t equals 4, not t equals 40, at what? B equals 40. So this first one is just going to be 1/5 times 100 minus 40 is going to be 60 over 5, which is 12. And what's that unit? Did they tell you what the units are going to be? Is it grams per day? Is it G per day? Yep. And what's dB dt? What's the next one you have to do when B is equal to? 70. So that's just going to be 1/5 times 100 minus 70 is 30 over 5, which is 6 grams per day. So when is it gaining weight faster? Faster at 40 grams. You just actually found it, right? Derivative, right. So what is the first derivative equal to? What is dB dt? 1/5 times 100 minus b. Before we take the derivative, what could we do first? Yeah, sure. So we know dB dt is equal to 20 minus 1/5 b. Sure. So what is the second derivative going to be? Negative 1/5. No, negative 1/5 of what? No. Negative 1/5 dB dt. You have to differentiate. B prime. You're differentiating with respect to time. You're differentiating with respect to time. So you can think of it as B prime. What is B prime? dB dt. But what is dB dt? So d squared b over dt, not d squared, but the second derivative in terms of time, and it's squared here. Sorry, thank you. So what's it? It's negative. Yeah, I'll get that in there. Hold on. So it's negative, right? So you end up with negative 1/5, 1/5, 100 minus what? B? Because that is, you take this right here, that it goes right there. Well, we will. I'm doing the substitution first. I haven't gotten to that yet. Okay, are we good so far? So could we keep going here? Sure. We can simplify it a little bit more if we want to. So what does that equal? Negative 100 over 25 plus what? Plus b over what? 25? Is that true? So what does it look like this is? This would be over dt squared is equal to 1/25 b minus what? 4. Derivative tell you about the graph? Concavity, it tells you about what? Concavity. It tells you about concavity. So the second derivative tells you about concavity. So what does this second derivative tell you about concavity? Okay, first of all, what are the values for b? We know that b has to be greater than what? 0, because the bird has to exist, right? Has to be greater than 0. Do you agree with that? Yes. Right? So another way to think about this is we could factor out negative 1/25. If we factor that out, it turns into b minus what? 100? Is that right? Negative b plus 100? Yeah, correct. So we end up with negative 1/25 times 100 minus b. That's another way to write out concavity here. What does it look like? There's a point of inflection right about there, right? So what does it tell us? It looks like it's concave down here and it's concave up right there. By what we have, b is, it looks like b is going to be less than 100.
So then b, or the second derivative is always negative, meaning that it's only concave down.
Now here's the thing that's important to realize. This is what's important to realize. This tells us the second derivative just in terms of b, correct? Do you agree with that? B is what? Is b time?
No, wait.
B is weight. B is weight, okay? So here's the thing. Here's weight, right? So do you agree that from 0 to b in less than 100, just like that, it has to be concave what? Cave down, right? This is the tricky part right here. So do you agree that when b is between 0 and 100, it has to be concave down? Where is b from 0 to 100? B is 0 to 100 from here all the way up like this. Look, the b value is on the y-axis here. Do you see that, everybody? This second derivative is just written in terms of the b value. But what do you notice? From 20 to something, what is that? Concave up. From 20 to something, it's concave up. But what do we know? It definitely should be concave down. So that's why you could say that. Just so the AP test, if they ask you to work with the second derivative and then they ask why can't this graph, why can't this graph match up? What does the second derivative tell you about? Concavity. That's an automatic key. I should examine concavity. So by far the hardest part for me, at least, is noticing that that graph that they give you, it has b on the y-axis. So you're looking at this and saying this is when b is greater than 0, and when b is greater than 0 and less than 100, always what? Concave up. No, guys, it's going to be negative. Concave down. But the graph is concave up for a portion of b greater than 20. Do you see that, everybody? We know it should be concave down the entire time b is above 0 and less than 100, but from 20 to like what? 40 or 50, it's concave up. So there's where it comes. When did we have to do this? We did a bunch of these. When we did it with slope fields. So we know that we're trying to find one solution. How many integrals does a given derivative have? Yeah, exactly. So in order to get one of them, what do you need? You need a condition. It's called an initial condition. So you know dB dt is what? 1/5 times what? 100 minus b. So what if we want to separate these variables? That's the first thing we need to do. What does it mean to separate the variables? We can multiply. Well, let's multiply it out first. We know dB dt is equal to what? 20 minus 1/5 what? B. So what should we multiply both sides by? dt. So we know dB is equal to 20 minus 1/5 b times what? dt. So therefore we know that 1 over 20 minus 1/5 b dB is equal to what? So we have separated the variables right there. All of the dB is attached to just b and constants, and dt is attached to just a constant. So now after we've separated the variables, what do we do next? No, we need to integrate. We're going up. We need to find the solution, right? So if we integrate both sides here, what do we get? ln of what? 20 minus 1/5 b times what? Times negative 5. Because it's going to kick out a negative 1/5, right? Equals what? T. Equals t plus what? Some constant, right? But we're not done yet, because what is it asking us for? Y equals b of t, right? So we need to isolate what? B. We need to isolate b here, right? Do you agree? We need to isolate b. So how do we do that? Well, we know that ln of 20 minus 1/5 b is equal to t plus c over negative 5. And I'm going to just clean this up a little bit first. I'm going to just call this t over negative 5 minus c over, or plus negative c over 5. Is that okay? So what do we now know? We know that e to the negative t over 5 plus negative c over 5 has to equal what? 20 minus 1/5 b. What do we still need to isolate here, right? So what are we going to do? I'm going to say d times e to the negative t over 5 equals 20 minus 1/5 b. Why am I allowed to just call that b? E to the negative c over 5 is just a constant. I'm just making a new constant. Yeah, it's annoying, but you can do it. It's annoying, but you're total. Yes, it's a constant. D is equal to e to the negative c over 5. It's a new constant. I just fashioned a new constant out of it. Yeah, they do it all the time. They just go, meh, constant. Yes, they do it all the time. Okay, so now what do we do? So we know that b is equal to d e to the negative t over 5 minus 20 over times what? Times negative 5, exactly. So we end up with b is equal to negative 5d e to the negative t over 5 plus what? Not dividing. You're right. Plus 100. We're not done yet. What do we need to find? Well, we have an initial. We need to find d. But what do we know our initial condition is? It tells us something. 0, 20 is a point. So when t is 0, b is 20. So 20 is equal to negative 5d e to the 0 over 5 plus, it's negative, but it's 0, right? So what do you end up with? 20 is equal to negative 5d plus, well, e to the 0 is 1, right? So that's why it went away. Negative 80 is equal to negative 5d, so d is equal to 16. So you end up with b of t is equal to negative what? Negative 80 e to the negative t over 5 plus 100. How many points do you think this one's worth? That section. You know how to take the derivative, the integral of f of x dx, correct? Yeah. That's what you know how to do. Yeah. That's the form you have to follow by.